Next we're going to move on to analyze the circuit, the RLC circuit. So we've got the resistor, the inductor, and the capacitor in a circuit. Let's look at how we're going to analyze this. And by analyze we mean let's try and get an equation for the charge on the capacitor plate as a function of time, just like we've done with the other circuits. Because once we have the expression for charge, we can find energy and all the other things, and current and the other things we want. So let's start with the switch flipped up. So here's our circuit. We've got a battery here, capacitor, inductor, resistor. We're going to start with the switch flipped up in A position. So we begin there. So begin switch at A. What does that mean? Well, if the switch is at A, this part of the circuit is broken. The battery is connected to the capacitor, so the capacitor is going to become fully charged. So our battery is a plus here, a minus here. This plate will become plus, this plate will become minus. This plate will have charge plus Q, and this plate will have charge minus Q. So that's what's going to happen. So the battery charges the capacitor. So that the net charges on the plates are plus and minus Q. The potential is across the plate. So it means that the net charge Q is the potential, epsilon, times the capacitance C. So that's where we start. Where do we go next? Well, at t equals 0, let's flip the switch down. So at t equals 0, let's flip the switch down to B. So now what that means is at t equals 0, this part of the circuit is broken, and this is the circuit we have left, the capacitor, the inductor, and the resistor. What's going to happen here is that the capacitor is fully charged. It's going to act as a supply of potential for the circuit. So the charge is going to flow, which means we're going to have a current flow. So at t equals 0, flip switch to B. And current is going to flow. Let's look at the direction of the current flow, and let's get that on our picture. We know that the positive charge are going to flow around the circuit this way. So our current flow will come around like this. Let's label that current flow I. So we're following the same sorts of analysis we've done on previous circuits. We're just including one more element now. So what we'll do is let's write Kirchhoff's potential law around the loop. So let's take our loop to go with our current. So there's our loop. Let's write down the potential law. I want a different color blue. Our potential law says that the net change in potential around the circuit is equal to 0. So we've got the potential on the capacitor, delta V of the capacitor, plus the potential of the inductor, plus the potential of the resistor. And we'll start off general and then we'll get specific. So the potential of the capacitor, it's a potential supply. It's got a potential of epsilon, which is equal to Q over C. For the inductor, we know that the potential across an inductor is minus the inductance times the change in current over the change in time. And across the resistor, we know it's a potential drop, so we have minus I times R equals 0. So now, it looks like we have two unknowns, but we don't really. We really only have one unknown. How do we deal with the Q and the I together? Well, we know that current I is change in charge over change in time. But for this circuit, we only get current flowing in this direction when the charge on the capacitor is decreasing. So the little bit of charge that moves through this circuit only happens because this charge decreases. So we can say I, which is dq by dt, is minus dq, the change in charge on the capacitor, by dt. So we've done that. This is the third time now, so hopefully that idea is okay. Let's put this in for our i's here. I'm going to try and be really careful and not drop my minus signs. It's really easy to drop those as you go through. Okay, so q over c minus minus L d minus dq over t minus, okay, got all my signs straightened up. Here we've got a minus and a minus for a plus, minus and a minus for a plus. Let's write that down next. D by dt times d by dt, that's the second derivative of charge with respect to time. So this is a second order differential equation. Let's just make this a little bit nicer before we worry about what the solution is. So the first thing I'm going to do is I'm going to get this d second derivative of q by itself by dividing every term by the inductance L. Q over L times C plus the second derivative of charge with respect to time. Plus, I'll bring my R out front, that's divided by L as well, dq dt, that equals 0. So now the next thing we'd like to do is let's neaten this up a little bit and put all the terms in order. So second derivative of charge with respect to time plus R over L times the derivative of charge with respect to time plus Q over L times C equals 0. Okay, so there's our equation. If I were really on top of my math game, I would be able to solve this off the top of my head. To be quite candid, I would need to brush up on these methods just a tiny bit. But the general solution to this equation is that charge Q is some maximum value, which we'd called Q0 in other problems, times e to the minus r over 2L times t times the cosine of the square root of 1 over LC minus r squared over 4L squared, that's times time. And if you want to allow for some starting other than at the amplitude, you can stick a phase constant in there. Okay, in our previous solution, we didn't put in a phase constant, but since we're gone general, let's put in our phase constant now. So Q0 and phi are constants. Let's see, so our symbols are R is the resistance, C is the capacitance, and L is the inductance, T for time, Q for charge, and Q naught for original charge, initial charge. Let's see, what's notable about this? So one thing you could do if you wanted to is you could either solve this equation for yourself with some of your math skills, or you could prove it was true by taking the second derivative of this equation, plug it in here, take the first derivative, plug it in here, and you would see that that equation holds to be true. So that's something you could do if you wanted to. That would hopefully prove to you that that equation is true. What are some other things we could do? Well, we said in the introduction to this course that the charge would oscillate as a damped oscillation, and here's how we see that damped oscillation. So right here, cosine of a frequency times time gives us an oscillation. Our exponential term gives us an oscillation that dies off. So we could make a plot of it. I suppose if you really wanted to, you could even put in the equation on an Excel spreadsheet, and you could have that plotted for you. So your plot would show an oscillation that gets smaller over time, and also your omega would change a little bit So your oscillation would be something like this, where this dotted line right here is the envelope of the oscillation. This part right here is equal to Q0, e to the minus 2 minus r over 2l times t. Shows it dies off over time. So that's one thing that's a little bit interesting. Another thing that might be interesting was we said this was the general solution to an RLC circuit. Well, what if the resistance was 0? Do we get back what we expected for an LC circuit? So let's look at that next. So what if R was 0? So then our equation, let's just plug in R equals 0 and see what we get. Q equals Q0, e to the minus 0, cosine square root 1 over LC minus 0 over 4L squared times t plus phi, that phase constant, which just allows for a start other than somewhere at the amplitude. E to the minus 0 is 1, so we get Q equals Q0 cosine square root 1 over LC times t plus phi. You might recognize this as the angular frequency in an LC circuit. Q equals Q0 cosine omega t plus phi. So if R equals 0, we recover the LC circuit equation. So that is good, and it tells us if we have a small resistance, so if in our circuit, if this resistance is pretty small, then this equation is definitely true, but it's approximated by this equation if your R is pretty small. And then the next part is, what about the frequency of oscillation? So the frequency of oscillation of the general solution, so for the RLC circuit, the frequency of oscillation is the square root of 1 over LC minus R squared over 4L squared. It's different because of the resistance. So this frequency of oscillation is not the same as the frequency of oscillation of the LC circuit because the resistance makes that frequency change. So that's a little bit different. And one last comment we might make is if we applied a sinusoidal force, so if we applied a driving force at the right frequency, we can again get a large amplitude of oscillation in the end. We can get a large response when we have a certain driving signal. That's what leads us to AC circuits. So if you apply a sinusoidal force, with the right frequency, you get resonance in your circuit, in your electromagnetic circuit, and then that resonance means you get the large response. That's where we get AC circuits coming from. In a regular semester, we would do lots of this, but our semester has been abbreviated by, my goodness, I think 6 lectures we lost due to snowstorms. So we're not going to get to do quite as much as we wanted to. So from here, we'll do a couple of examples of RLC circuits, and then we'll call that enough. We'll call it quits there.